Hello guys, how are you today? So today I'll be explaining the past papers for physics, and I'm gonna start with the October-November 2021 paper 42. So a thermocouple thermometer is used to determine the temperature difference between a mixture of ice and water and liquid mercury at approximately 600 degrees Celsius. So they need us to complete figure 5.1 with a label diagram to show how the thermocouple thermometer can be used in this way. So I'm going to draw it first, then I will explain to you how I drew it. Okay? Then this comes here. Then this comes here. Now what we have over here is a thermocouple thermometer. This is made out of A, this is made out of A, this is made out of B, and this is blue is a galvanometer. Now what you need to know is that the two wires coming out of the galvanometer have to be the same material. And then the wire that connects them is made out of a different material. So if you make wires, of two different materials, that's 1 point. Now, this terminal, the end of this thermocouple, they both have to be each in different liquids. And you have to include the galvanometer or voltmeter or ammeter. And if you put these three, you are going to get all 3 points. Now, state two other physical properties that can be used to measure temperature. One physical property is the expansion of a liquid. You can see this in thermometers. So as the temperature increases, the liquid volume increases, and as it decreases, the volume decreases. And another thing is the electrical resistance. So some of them can create a resistance in the electricity, for example, in the thermocouple. And this is how you get 2 points. So you can state the expansion of the liquid, the density of the liquid, the electrical resistance, anything that can be used to measure temperature because they are thermometric properties. Now state two benefits of using a thermocouple thermometer instead of a liquid and glass thermometer. We know first of all that a liquid and glass thermometer cannot handle high temperatures, so we can say a large range, meaning it can measure extremely high and extremely low. Another thing is that it has a low thermal capacity, meaning at the slightest change it will notice it. Other benefits could possibly be that it responds quickly, it measures really high temperature, it's small, and it's very useful and compatible to use. Now we move on to the second question from this paper, which is question number 8. Now, the figure shows a conducting object A initially uncharged, meaning it has the same positive, let's say 3 positive, and the same negative, 3 negative, held on an insulating stand. The positively charged rod B is brought close to object A. So what's gonna happen now is that the negative charges are gonna accumulate next to the charged rod B, whereas the positive charges are gonna repel and go to the other side. Now, no, the positive charges cannot move out of the object, they can only stay inside of the object. So this is part 1 done. Now, what exactly do we need to get the 2 points? First, you have to make sure that there are more negative on the left side, more positive on the right side, and they have to be equal in number because it was initially neutral. Then, for part 2, a wire is connected from object A to Earth. So let's say they connected a wire. They are doing grounding or earthing. We need to state and explain any movement of charge. Very simply, since the positive charges cannot move, then the negative charges are going to come from the Earth and into the uncharged object to the positive side because it needs to balance it. So what do we state? We can state that electrons or negative particles flow from the Earth and they flow towards the positive charge. Now, why do they flow? They flow to balance the positive charges on the object. And like that, you get the whole 2 marks. Now, for part B, there is a current in a wire of 0.65 milliampere for 2.2 minutes. We need to calculate the charge that flows. You have ampere, which is the current, the time, and you need to find the charge, which is Q. What is the equation we can formulate? We can formulate that I is equal to Q divided by T. So I, you need to change it into amperes. It will become 0.65 times 10 to the negative 3 amperes is equal to the charge Q, which we denote by Q, divided by the time in seconds, so times 60 seconds. Solving it, it's supposed to be 0.65 times 10 to the negative 3 multiplied by 2.2 times 60. If you solve it on your calculator, you are gonna get 0.0858. But then you need to round it to two significant figures, so 0.086 Coulomb. Do not forget the charge. Now, to get the full 3 points, you need to state first this equation, then you need to substitute this equation, and then you need to put the final answer. So this is part B. Moving on to question number 4 in the new past paper. So in October-November 2020, past paper number 42, we have question number 4 and 5. So question number 4, figure 4.1 shows a thermometer. Looking at it, we need to state the name and type of this thermometer. Now, if you notice, we have wire of a material A, then wire of a material A again. We have a voltmeter, and we have a different type of wire. So if you remember what we did in the previous one, then we can say that this is a thermocouple. All right, so the name of this type of thermometer is a thermocouple. Now, figure 4.2 shows the same thermometer used to measure the temperature of liquid X. We need to calculate the temperature of liquid X measured by the thermometer. So let me zoom out for a second. We need 2 points. To get these 2 points, what we are supposed to do is remember 2 equations, or not write 2 equations, to solve twice. First time, we need to write the equation to find temperature final. It is equal to temperature initial plus the change in temperature. We have temperature initial, which is 20 degrees Celsius, plus the change in temperature, which we will find. Now, to find the change in temperature, very simply, we can say that at 5.4 millivolts, it gives us a change of temperature, which is 100 minus 0, which is 100. So how much will we get at 1.7 millivolts? You do cross multiplication. So then it is 1.7 times 100 divided by 5.4, and you are going to get 31.48, which is approximately 31. We will take it as 31. So 20 plus 31 degrees is then going to give us 51 degrees Celsius. If you write 1, 2, and 3, then you are going to get the whole 2 points. Okay, so now we move to over here. We need to suggest an application for which this type of thermometer is more suitable than a liquid in glass thermometer. So basically they're asking us, in which situation would the thermocouple be more suitable to use than a liquid in glass thermometer? We should know that liquid in glass thermometer cannot withstand the high temperatures or low temperatures. So you can write whenever measuring extremely high or extremely low temperatures. All right, now we move on to question number 5 of the same paper, and we need to define specific latent heat. We need 2 marks for this. To get the 2 marks, the first thing you are going to state is that it is the energy needed to change the state, and like that you get 1 point. Now the state of what? Of 1 kg of a material. So the specific latent heat is the energy needed to change the state of 1 kg of a material. Now the specific latent heat is different from the specific thermal capacity. If you want to define the specific thermal capacity, it's the energy needed to change the temperature of 1 kg of a material by 1 degrees Celsius. However, specific latent heat is the energy needed to change the state of 1 kg of a material. So this itself is 1 point, and this itself is another point. So 2 points. Part 2. Explain the melting of a solid in terms of molecules and energy. Now, the melting of a solid in terms of molecules and energy. We can say, to get 2 points, that a solid has bonds that must be broken, okay? And for these bonds to be broken, we need energy. So you get 1 point for saying that a solid has bonds that must be broken, and another point for saying that we need energy to break these bonds. Now, if we move on to part B, we have an electric heater is used to heat a liquid to its boiling point. Figure 5.1 shows the apparatus. When the liquid is boiling, the heater supplies 1.26 megajoules of thermal energy. The mass reading shown on the balance decreases from 3,800 grams. What we need to know is that the specific latent heat of vaporization of the liquid, which is denoted by LF, or not LF, sorry, LE, it is equal to the mass multiplied by, whoops, okay, I don't have a marker, there we go. We should know that the specific latent heat of vaporization of the liquid, okay, which is denoted by E, energy, it is equal to the mass multiplied by the specific latent heat of vaporization. So the energy needed, or the heat needed to vaporize this liquid is equal to its mass multiplied by the specific latent heat of vaporization. So for this one, you're gonna get 1 mark. Now, we need to find the mass. We are given in grams, but in physics we always change to kilograms. So it becomes 3.8 kilograms and 2.3 kilograms. But we're not gonna take these values, we are gonna subtract them. So it becomes 3.8 minus 2.3 kg, and that is 1.5 kg. Okay, for this you get another point. Now for the final one is to substitute. They gave us the heat used, which is 1.26 times 10 to the power of 6 because it's in megajoules, multiplied, or sorry, not multiplied, this is the energy, is equal to the mass, which is 1.5 kg, multiplied by the specific latent heat. So then to find the specific latent heat of vaporization, it becomes 1.26 times 10 to the power of 6 divided by 1.5. So then 1.26 times 10 to the power of 6 divided by 1.5, we are gonna get 840,000, and then if you want to put it in scientific notation, it is 8.4 times 10 to the power of 5. So this you get the final point, which is point number 3. The answer is, by the way, 8.4 times 10 to the power of 5. Now state and explain a precaution to improve the accuracy of the value of specific latent heat. What we can do is to insulate it to prevent any heat loss. So prevents heat loss. You get 1 point for saying insulate and another point for saying prevent heat loss. Now we move on to the next paper, which is October-November 2019, paper 42. And we have question number 4 in it. Now, a student carries out an experiment to determine the thermal capacity of a metal block. The block is heated by an electric heater for 23 minutes. The current in the heater is 3 amperes. We have the current I at a potential difference of 12 volts. So we have the voltage. The temperature of the block rises from 20 degrees Celsius to 70 degrees Celsius, so delta T is 50 degrees. We need to calculate the thermal capacity of the block. Oh, and by the way, I forgot here, 23 minutes. So you have to multiply it by 60 to get it in seconds. And 23 times 60 is 1380. Now, what we know is that Q, which is the heat, is equal to I, V, T. I is the current, which is in this case 3. V is the voltage, which is in this case 12. And T is the time in seconds, which is 1380. So you multiply them together, and you are going to get 3 times 12 times 1380, 49680. Okay, so we are going to use this. Even though they rounded it in the answer key, I prefer to use it like this, 49680. Alright, now here, this is where it gets tricky. They did not mention anywhere mass, so we are going to say the mass is negligible, meaning we are going to forget about the mass for now. If we forget about it, it doesn't mean it's zero. It means the equation is now without mass. It is now that Q, before it was Q equals MC delta T. Now Q is equal to C times delta T. Because they did not mention any mass, so the mass becomes negligible. So the Q, which in this case we got it to be 49680, is equal to the C that we need to find times delta T, which is 50. So bring it to the other side, you are gonna get 49680 divided by 50, which is approximately, the value of C is gonna be approximately 994. Now the unit is joules in J per degree Celsius. Now I know in the answer key it's different, but this is with the exact numbers. In the answer key they rounded it. Alright, so they told us it's 4 points, so this is a point, first of all, for solving this, then a point for solving this, and a point for getting this answer, and then finally a point for getting this answer. So 4 points. Now we move on to part B. They told us 2 metal spheres of different diameters are heated to 900 degrees Celsius in a hot oven. The 2 spheres are removed from the oven. State and explain any difference in the initial rates of emission of radiation of thermal energy between the 2 spheres. Now what we need to know, since they have different diameters, then definitely there is a larger one. Both of them are heated to 900 degrees Celsius. So that means definitely the larger one is gonna absorb more, but then when it goes out, it's gonna lose more because it has a greater surface area. Okay, so we need to state and explain. Stating is one thing and explaining is another thing. So what's gonna happen is that the larger sphere loses more heat due to its greater surface area. Now, in part 2, so this is part 1 of B, in part 2 of B, one hot sphere is now heated in a hotter oven. They told us, state and explain any effect on the rate of emission of radiation of thermal energy from that sphere when it is removed from the hotter oven. Now, because it is hotter, it is definitely gonna have a greater rate of radiation emission because it possesses more heat due to its possession of greater heat. Okay, and this is it for this paper. Now we move on to the next one. Now, a machine delivers a hot drink in a plastic cup which is uncomfortably hot to hold. Figure 5.1 shows the cup with the hot drink. Figure 5.2a shows the cup with the hot drink and a holder for the sides of the cup. Figure 5.2b shows a cross-section through the holder. The holder is made from 2 strong paper cylinders separated by wavy piece of strong paper to make air gaps. Now, explain how using the holder makes it more comfortable to hold the cup. Very simply, listen, you have to keep in mind about the keyword. You have air gaps. You know air is a good insulator. that means it will prevent the heat from emitting out of it. So the first thing we got from this is that the air is a good insulator. Now, another thing we need to write is that there is less thermal energy, or let's just say heat, less heat conducted to the hand. This is our second point by saying because air is a good insulator, less heat is conducted to the hand. Now, finally, the thing we need to know is that the temperature outside of the holder over here is less, definitely it has a less temperature than the cup. So the three things we need to say to get 3 points is that first, air is a good insulator, then less heat is conducted to the hand, and temperature outside of holder is less than the cup. And that is how you get the 3 points. Now we move on to part B. A student carries out an experiment, or not an experiment, experiments on the cooling of the hot drink described in A with and without the holder in place. He finds that the holder only reduces the rate of cooling slightly. Suggest and explain another action that reduces the rate of cooling more effectively. Now, suggesting and explaining are two different things. Suggestion, you choose only one thing. Explanation, you have to explain 2 things to get the 3 points. So a suggestion is possibly putting on a lid. Okay, this is very logical. It will reduce the area by which the heat can escape. So one thing you can write is it reduces the heat for the it reduces the area by which the heat can escape. It's not an option, so keep it in mind. Another option they put is that no convection happens. Convection happens due to the lid, and no evaporation happens as well. So if you state these 3, you are gonna get then 3 points. Now, part C, state the method of thermal energy transfer from a star through the vacuum of space. The keyword is vacuum. The only type of method of heat moving is radiation. If it is in vacuum, then the only type of thermal energy transferring in vacuum is radiant energy or radiation. Okay, now we move on to the next past paper, which is May-June 2020. We start with figure 4.1 shows a liquid in glass thermometer without a temperature scale. The liquid inside the thermometer has a melting point of minus 39 degrees Celsius. Describe simple experiments to mark the positions of the fixed point on this liquid in glass thermometer. 4 marks, meaning we have to describe, like state one experiment and describe what happens. State another experiment and describe what happens. So the first one is to get is by calibration, okay, to get the melting point. So to get the melting point, you need to place in melting ice. For this, you get 1 point. Then another point is that you have to mark the fixed point by putting it in melting ice. So mark the fixed point by 0 degrees Celsius. Now, if we are talking about the 100 degrees, you need to place in boiling water. Not in, actually above boiling water. So you place it in the steam of the boiling water. Steam of boiling water. Then, to get the final point, you just need to say mark the fixed point by 100 degrees Celsius. And that's how you get 4 marks for this question. Now, part B. A scientist is measuring temperatures at the South Pole. The temperatures have a minimum value of minus 90 degrees Celsius. State why the liquid used in the thermometer in figure 4.1 would not be suitable for this scientist. They told us that the liquid inside of this thermometer has a melting point of negative 39 degrees Celsius. And we should know that the melting point is also the freezing point. So at negative 39 degrees Celsius, it becomes a liquid. So what we can say is that the liquid inside thermometer would freeze. Okay? Part C, state a design change that increases the sensitivity of a liquid in glass thermometer and increases the range of a liquid in glass thermometer. Now, to increase the sensitivity, one logical answer would be to use a thinner tube, so then it's more exposed to the temperature outside. Now, to increase the range of this liquid, we can use a longer tube. So if you write these, you will get 1 mark and 1 mark. Now state the property of the liquid which ensures that the scale on a liquid in glass thermometer is linear. It is the expansion of the liquid uniformly with the temperature. So what you can say is that the liquid expands uniformly with temperature, meaning an increase in temperature will cause the liquid to expand. Now we move on to the next one, which is question number 10 in the past paper May-June 2018, paper 42. An uncharged conducting metal plate rests on insulating supports. Figure 10.1 shows the plate and a positively charged insulating plastic sheet placed on top of the metal plate. We need to describe any flow of charge that takes place when the plastic sheet is placed onto the metal plate. Now, the plastic sheet, they told us, is positively charged. So then, if this is uncharged, meaning it's neutral, so let's say it has 2 negative, 2 positive, then the negative charges are going to move towards the positive charge. So you can say negative charges move towards the top. Okay? Now, on figure 10.1, draw how the charges are now arranged within the metal plate. So now, the negative charges are going to be in the top. So let's say we have 1, 2, 3, 4, 5 negative charges. Then at the bottom, we would have 1, 2, 3, 4, and 5 positive charges. Okay, they should be the same number of charges, okay, and more negative on the top. Okay, now, in part 3, state and explain if this arrangement of charge helps to keep the plastic sheet in place. Now, definitely, it does allow the plastic sheet to stay in place due to the force of attraction between the opposite charges. So what you can say is yes, because this is a statement. Then you can continue on, the plastic sheet stays in place because negative and positive or opposite charges attract. Now, if we move to the next page, we have part B. Figure 10.2 shows 2 uncharged conducting spheres suspended on insulating threads. The spheres are now both given positive charges. Okay, so now this is positive and positive charge. On figure 10.2, draw a possible position of each sphere and thread. Now, a possible position of the sphere and thread is like this and like this. Because they are of the same charge, they are going to repel each other, so they're going to diverge away from each other. Now, they told us, explain the positions we have drawn. We can say, because like charges repel. And that is it for this page. Now we move on to this last paper. The final paper is May-June 2020, but paper 43. Okay, we have question number 4. Describe in terms of molecules what happens when a liquid evaporates. Now, when a liquid evaporates, we have to mention that it's only the molecules from the surface of the liquid that evaporate. So we have 4 points. You will get 1 point for saying that molecules of surface of liquid will escape. Okay, you will get another point for saying that the molecules that move faster escape. Then the slower molecules stay behind. And then finally, the temperature of our liquid will decrease because the average kinetic energy decrease. So what happens when a liquid evaporates? First, you have the liquid over here, and you have the particles like this of a liquid. They're not too close and not too far. So then the top particles will definitely escape. Then the particles that are like more inside, the ones with more kinetic energy, move faster. The slower molecules stay behind. And because the ones with more kinetic energy move faster, and they escape, okay, they will leave the slower behind, and then the average kinetic energy will decrease, which will then cause the temperature of the liquid to decrease. Now for part B, figure 4.1 shows wet clothes drying on a washing line in an outside area. State 2 changes in weather that help the wet clothes to dry more quickly. Now, for the clothes to dry more quickly, there's definitely supposed to be more wind, so it can carry the water particles, or the temperature increases. And that is how you get both points. Now we move to the next one, which is number 5. Figure 5.1 shows a plastic cup. The cup contains sand, an electric heater, and a thermometer. Okay? The power of the heater is 50 watts. Keep this in mind. Power. The mass of the sand is 550 grams, which is 0.55 kg. The initial temperature is 20 degrees Celsius. The heater is switched on for 2 minutes, which is 120 seconds. The temperature is recorded until the temperature stops increasing. The highest temperature recorded by the thermometer is 33 degrees Celsius, so temperature final. We need to calculate the energy supplied by the heater. Very simply, the energy supplied by the heater, which we can denote by Q, we can find it in many ways. We have Q equals MC delta T, Q equals MLF, Q equals MLE, and then Q is equal to power times time. Here we have power and we have the time. So we can use the power and the time. So Q is equal to the power, which is 50 watts, multiplied by the time, which is 120 seconds. It's going to give us 6,000 joules. So the energy, you will get 1 point for this, and then the energy, which is then 6,000 joules. Okay, now for part B, for part 2, they need us to calculate a value for specific heat capacity of the sand. We have the energy, which is 6,000 joules. We know it's equal to m times c times delta t. We have the mass, which is 0.55 kg, multiplied by the c, which is what we need to find, multiplied by the change in temperature, which is 33 degrees Celsius minus 20 degrees Celsius, which is then 13 degrees Celsius. So then, after making it an equation, you're going to get that c is equal to 6,000 divided by 0.55 times 13. So 6,000 divided by 0.55 times 13, and you're then gonna get 840 joules per kg times degrees Celsius. So you found C to be 840. Originally it's 839, but then you round it becomes 840. Now part 3, explain why the specific heat capacity of sand may be different from the value calculated in part A2. You need to give 2 reasons. You can either say that some heat may be lost to surroundings, or some heat may be gained by surroundings. So if you state these two, you are gonna get the 2 points. Now we move on to part B. On a sunny day, the temperature of the sand on a beach is much higher than the temperature of the sea. We need to explain. You can say that specific heat capacity of water is probably higher than that of sand. So that means if the temperature is the same for both of them, or the heat is given same for both of them, then definitely it's gonna be higher. So we can say same heat given, and that's 2 points. So let's explain again. So if the specific heat capacity of water is greater than that of sand, okay, and the same heat is given, then definitely the temperature of sand is higher than the temperature of the sea. Now draw a labeled diagram to show the structure of a thermocouple thermometer. Again, you need to draw, for example, 2 cups, cup 1, cup 2. Say this is cold, this is hot. Okay, then you bring over here, like this and like this. I wrote this wrong. Like this and like this. Okay, then you draw another wire over here, and then you draw the galvanometer over here. And you have to state that this wire is different from this wire, and you have to show that this is a galvanometer. And that is it for question number 5. Now we reached question number 8, which is the final question. We have only parts A and B. We need to describe what is meant by an electric field. Very simply, an electric field is the region or the space in which an electric charge experiences a force. Okay, now state what is meant by the direction of an electric field. It is very simply, it is the direction of the force it would put on a positive charge. So very simply, the direction of an electric field is the direction of force on a positive electric charge. I don't know if I said it before, but again, the direction of the field is defined by the direction of the force it would put on a positive charge. Okay? So that means that the positive charge goes in the same direction of the electric field, whereas the negative charge goes in the opposite direction of the electric field. Now, if we move to part B, figure 8.1 shows a polystyrene ball covered with an aluminum paint. The polystyrene ball is suspended between 2 charged metal plates by an insulated thread. Okay, the ball oscillates between the 2 charged plates. Explain why the ball oscillates. Okay, so this is actually an interesting question. So look what's gonna happen. We have this neutral charge. Let's say we have 1 negative, 1 positive. And let's say initially it is attracted to the positively charged metal plate. So it's gonna move and it's gonna be like this, and the negative charge is here, whereas the positive charge is over here. But when they touch, what's gonna happen is that by conduction, the positive charge is gonna move over here. Okay, so now it has more positive charge. Actually, theoretically speaking, we cannot move the positive charge. So let's say the negative charge will move out of the ball into the positively charged plate. So that leaves us with a positively charged ball. We have positive and positive, they are going to repel. So the ball comes back to the center. Now, because it's positively charged, it's going to move towards the negatively charged plate. So positive charge over here. It is going to touch it, and some of the electrons are going to move. So then it becomes negatively charged. And so then it's going to move back to the positive, it's going to become positively charged, move back to the negative, become negatively charged, and it continues like this, so on and so forth. So if we want to explain it in terms, very simply, we are going to say that the neutral ball is attracted towards the positive plate, it touches the positive plate and becomes positively charged. Then it is attracted to the negative plate, then it touches the metal plate and becomes negatively charged. So let us state it like this. Neutral ball is attracted to positive plate. Okay? Touches the plate, then becomes positive. Then we go to a new one. Positive ball attracted to negative plate, touches plate, becomes negative. Then we are gonna write one more line. This is the final line. Negative becomes, my bad, I'm writing on my tablet, that's why my handwriting is bad, becomes attracted to positive and cycle, causes oscillation. And that is it for the past papers. Thank you guys for watching, and I hope you enjoyed.